So we've been computing Riemann sums, and as you know, we're using a tool made with GeoGebra that will compute the Riemann sums for us. It'll draw the pictures, graph the function, and draw in the approximate area under the curve. Unfortunately, the tool that we were using does not compute Riemann sums that use the midpoint for the representative x value. So I found a tool that does use that, and I'll link to it in the Blackboard, but I want to show you right now how I can do problem 13 here, x squared plus 1 on the interval 0, 2 with 5 rectangles, and I'll use midpoints to compute that. So if I go to the tool, this tool happened to be made by Desmos, not by Desmos, but with Desmos. And so what we do, I'll just kind of show how this works. We're going to first enter the function in, and our function is x squared plus 1. Okay, so we get that function in. You can see that it's drawn a bunch of rectangles and it's approximating the area under the curve. That value actually shows up here. They've called that I. Okay, so I is where our answer pops up. To make this tool work with the problem that we're working on, we need to enter the endpoints, the number of intervals, and the method that we want to use. So I'm going to click this arrow here. It drops down. And you can see I've got a slider here where I can enter the value of A. Since we are on 0, 2, A is going to be 0. B needs to be 2. So I'm going from A to B, 0 to 2. Probably need to zoom in a little bit on this. There we go. And right now you can see it looks like we're computing these rectangles using the left-hand endpoint. And we're doing 19 rectangles. So first of all, let me crank this down to 5. N is the value for the number of rectangles. So now I'm down to 5, and then you'll see here it says choice of method. A 0 is for left-hand endpoint, left-hand sum. A 1 is for right-hand sum, and 0.5 is for the midpoint. So you watch how these rectangles change as I slide this. If I go to 0.5, it does the midpoint approximation. If I go to 1, it does the right-hand approximation. It's kind of cool how you can see how these approximations vary. For the function x squared, the left-hand endpoint obviously misses quite a bit of area. The midpoint does a pretty good job, and then the right-hand endpoint is too high of an approximation. It's above the curve at every point on this interval. So you can see how we can slide to pick the method. So I'm going to use the midpoint method, and sure enough, down here at the bottom, letter I is my value for the approximate area under that curve, or the approximate value of the interval is 4.64. So if you have a problem where you want to use the midpoint as a representative value, you can use this tool, and it'll give you the Riemann sum. It draws the picture, it gives you the value. It's pretty cool. Just want to show you one more thing before I let you go. What we're going to be doing as we move forward in our study of area under the curve is we're going to be eventually trying to improve this approximation. And you can see as we increase the number of rectangles, we get closer and closer and closer over here to the actual area under the curve. And by increasing that number on the computer, you can see that it basically makes the rectangles disappear because they're so thin. That process is called the limit process. And while I can only go to 100 rectangles with this tool, the idea is that with calculus, we can send the number of rectangles to infinity, and we can get the actual area under the curve. So that'll be our goal as we continue to study this concept. For now, computing Riemann sums gets a little bit easier when you have tools like this to use. So good luck. Keep the questions coming. Take care.